Next, we are going to introduce another concept, that is array efficiency. So the array efficiency is defined as the area percentage occupied by the memory cells on the chip. So let's look at the generic organization of the memory chip. So here you see this box is called the memory cell array. And this is the area where the memory cells really occupy. And the memory cell array is typically organized in the rows and columns. So you have many rows and many columns. So each intersection here is one memory cell. So you have many memory cells in this array. And also the row is called the word line, WL, this word line. And then the column is also called the bit line. And here, how many cells are in this array? So by the way, here this memory, so here we are talking about the generic architecture. So this memory cell here can be either SRAM or DRAM or flash. We're going to discuss those memory cells in more details later. But no matter which memory cells, the overall architecture for the memory chip will be similar like this. So you have those rows and columns. So here we're going to discuss the address bits to control the row and column. So here the input to the memory chip will have this bits. And in this case we have n plus m bits. So the n bits is for the row address. So here is n bits is for the row address. And then we need to go through this module called the word line decoder to decode the n bits input, that is address, to the actual number of rows. So how many rows, how many word lines here? So if it's n bits input, then the output will be 2 to the power n. So for example, if it's 10 bits input as a row address, so that means you have 10 inputs here, and then the output will be many. So how many? You will have 2 to the power 10. 2 to the power 10 is 1024, 1024. So you can use 10 bits to control 1024 rows, and then giving a certain address, you are going to turn on or activate one row, so you can locate the data in that row. And similarly, we need the column address, m bits here. So this m bits is for the column decoder, and then this will identify which column you are going to select. So we need to use our multiplexing to select which column we want to read the data from. So again, for example, if you have 8 bits, then here 2 to the power 8 columns will be 256. So here I just want to emphasize that the column bits is to locate a group of columns. So here let's say we have a group of columns, and then that is k columns, k bits as a column group. So here actually what we are decoding is to decoding the column group. So for example, we have 8 bits as a column address, and we're going to decode 256 column groups. And every time when you decode one group, you are going to read out those data simultaneously. So here we have k bit data read out simultaneously. So the k, for example, can be 8. So that means every time we are going to read out 1 byte. So if k is 8, then every time when we activate one group, we are going to read out the data by 1 byte. So overall, the number of bits is first number of rows, that is 2 to the power n, times the number of column groups, that is 2 to the power m, and each group we are going to read out k bits. So that is 2 to the power n times k times 2 to the power m bits. So this is how we organize the memory chip. So here, as you can see, that in the whole memory chip, the area percentage occupied by the memory cell array. This is memory cell array. But you have other modules. So those are called the peripheral circuitry. So this is the peripheral. So the array efficiency is defined as this shaded area, which is the memory cell array divided by the total area. That is this array efficiency. So here in the peripheral circuitry, what do you have there? You may have this address decoder, like word line decoder, column decoder, and this column multiplexing. So this is just to identify or locate individual row and individual column group. So you can find the data you want. And then we may need those sense amplifier to read out the data. So the sense amplifier we are going to discuss briefly later in the S1 or the DRAM lectures. This is to sense the voltages in small signal. Like you store 0 or you store 1. When you read out the data, you are not going to read out the digital data right away. You read out some analog voltage, and then you need to amplify that voltage to digital 1 and digital 0. So the sense amplifier is for that job. And write driver is when you need to write the data in, then you need to basically drive the data along the wires. You need some driver, basically buffers, in a chain of inverters to drive the data in. So you need those peripheral circuits to assist you to read and write the data. And then some charge pump for high voltage generation on chip. So some of the memories, for example, the flash, you may need 20 volts for the write. And your power supply may be today like 1 volt power supply for the chip. But you need to generate 20 volts out of 1 volt. And then you need some charge pump circuitry to boost the voltage domain from 1 volt to 20 volt. So you need those peripheral circuits to do those jobs. Therefore, the array efficiency is the percentage of the area that occupied by the memory over the total chip area, which includes both the memory and the peripheral circuitry. All right, any questions here? Why is number of output a power of 2? Because the decoder's job is to decode the signal in the binary format to the natural number. So the binary number, if you have 1 bit, means 0 and 1. 2 bits means 0, 1, 2, 3. 3 bits means 0 to 7. So it's decoding process. So it's 2 to the power something. It's just a binary encoding and decoding process. So that explains why the memory array is always those numbers. I can remember those numbers. 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. So those are the typical numbers for the number of rows and columns. Okay, so then let's look at one real example from the industry. So this is 32 nanometer processor from Intel, and this is the image of the processor under the microscope. So in this case, we have a 6-core processor. So you see here 6 core. And in total, we have more than 1 billion transistors on this chip. And here the L3 cache is labeled here. So the L3 cache is shared between so this part is shared by core 0, 1, 2, and this part is shared by 3, 4, 5. And the L2 cache is private. So here this is probably the L2 cache. This is L2. It didn't label, but it's here. And L1 is much smaller, so you cannot see it. So here, let's look at the characteristics of the L3 and L2 cache. So in total, here we have 12 megabytes L3 cache. And each L3 cache memory is made of 6 transistor SRAM cell, and each of the SRAM cell occupy 0.171 micrometer square. This is for one cell. And actually you can normalize that to the F square as we discussed earlier. We can do that. So if you normalize that, so one cell is 0.171 micrometer square. So here the F is 32 nanometer. So F squared is 32 nanometer squared. So we need to change it here. Let's do it with the micrometer. So 32 nanometer is 0.032. 0.032. Right. So then I think I've done this. So if you do this, 0.171 divided by 0.032 and then 0.032. So if you do that, it's 167. So this is 167 F squared. So this is close to what we discussed earlier. For the SRAM, L3 cache is close to 150 F squared. So in this particular design by Intel is 167 F squared. And you can calculate for the L2 cache if you wish. So it's larger than this one. This is the cell area in terms of F squared. And also from this example, we can estimate the array efficiency. So we can do the array efficiency calculation for the L3 cache. So how do we do that? So the L3 cache is here. The array efficiency of the L3 cache means the area percentage occupied by the SRAM cells over the L3 area in total, like this, in total. So here, probably those are the SRAM cells, but you have those peripheral circuits as we discussed. So we can estimate using the following method. So first of all, here, the SRAM cell size we just discussed, one cell is 0.171 micrometer square. And how many cells in total? So we say this is 12 megabytes L3 cache. So 12 megabytes, we have to convert to bits because 1 byte is 8 bits, and one cell store 1 bit. So this is 96 megabits. Then the area of the SRAM cell will be this 1.171 micrometer square times 96 megabit, and 96 megabit is close to 96 times 10 to the power 6. 1 mega is close to 1 million, so it's 96 times 10 to the power 6. So that is the area of the SRAM cell. So the efficiency, array efficiency, should be this area divided by the total L3 area. So the total L3 area, so here, I think from the spec of this chip, the total area, total CPU area is given. It's 240 millimeter square. So 240 millimeter square. And L3, so here we have to maybe use a ruler to measure the percentage of this L3 region over the total chip. So if you do that, it's about like 26% of the total CPU area. So if you do that, so here then this one will be the 240 millimeter square times this 26%. So basically the array efficiency will be the numbers here divided by the numbers here. So if you do that, you will get the eventual percentage. It's like 27%. So this is pretty low for the SRAM. And if you look at the array efficiency for the DRAM or for the NAND flash, that will be even higher. For DRAM, you can approach 50%, and for the NAND flash, you can approach like 80%. So this is just one practice using this Intel's chip. So any questions? All right, next we are going to discuss about the memory hierarchy, why we want to have different levels in this hierarchy. So as you can see from the earlier examples, the smaller capacity, like L1 cache, is very fast. But the larger memories, like the flash, you can have 1 terabyte, but it's very slow compared to the SRAM. So to have a good balance between the speed and the capacity, then we have to introduce multiple levels in the hierarchy. This is why we have this memory hierarchy in the system, because there's no single memory that can satisfy both fast speed and large capacity. And then here we are going to introduce the principle that is used in the cache. So the cache is to store temporal data, and those data are frequently used by your CPU core. So here the principle is based on the locality. So we have the temporal locality and spatial locality. So the temporal locality says that if you did something, it's very likely that you will do the same thing again. For example, if you often join our live session in the past weeks, it's very likely you will do the same for the future. And spatial locality, if you did something, it's very likely you will do something similar next to each other. So this is true because in your software program, the nature of the program typically composed of many loops. So if you look at the simple code for the for loop, here you are going to access the data from the memory using both temporal locality and spatial locality. So temporally, here you have the variable. That means there's a memory location to store the partial sum. So you are going to fetch this sum and then add the new data and then store it back. So you are going to use this partial sum temporally. And spatially, you are going to add the new data, but those new data in the consecutive locations, because here you move the index by 1. So it's very often that in the computer program, you are going to access the data using this temporal and spatial locality. That means you can predict what data you can save in the cache. Therefore, you can get the data very quickly. Then we can have this hierarchical latency analysis in the memory hierarchy. So for a particular level I in the hierarchy, we have the technology intrinsic access time Ti, so small ti. And then we have the perceived access time, big Ti. And this big Ti is typically longer than the intrinsic access time. Why? Because when you look for the data in the level I, you have two possible outcomes. One is the data is there, so you find the data. We call it hit. So you hit the data in the level I, and then you need to spend the access time, which is intrinsic access time Ti, the small ti. But there is a chance that you miss the data there. That means you cannot find the data you want to use in the level I. That means probably your data is in the next level, level I+1. So you need to first look for the data, that is the small ti. If data is not there, then you need to look for the data from the next level. So you need to spend the perceived access time for the next level, big Ti+1. So overall, the perceived access time for this level I will be big Ti here equals to, if you hit the data, Hi times small ti, plus if you miss the data, Mi times the time you need to fetch the data from the next level. So here, because you either miss or hit, so the probability here, when you add Hi plus Mi, it will be 1. So here you can rewrite this a little bit. So here Hi plus Mi Ti, so this is 1. So that's why you have this equation here. So this is a recursive equation, because for the level I, the perceived access time, you need to use the perceived time for the next level. And here we have the miss rate, that is the probability you miss the data. So here this is the equation as we just derived. Of course, ideally you want the perceived access time the same as the intrinsic access time. So the big Ti close to the small ti. To achieve that, then you need to minimize this part. So you can keep the Mi low. That means you need to reduce the miss rate. How do you reduce the miss rate? One way is to increase the capacity of this level I to lower the miss rate, Mi. The reason is that if you have larger capacity of this level, then you can store more data on this level. So it's more likely you are going to find the data you want to use in this level. So the Mi will be reduced. But be aware of increasing the intrinsic access time for the level I. The reason is that you have larger capacity, then you need longer time to locate the data in this level. This is simply because if you think about the memory array size, we have the rows and columns, right? Now you increase the capacity, it's like you increase the size of the memory. You have more rows and more columns, so the wire distance is going to be longer, right? So when you access the data, you need to basically have the input like the row address, and then you apply the voltage here, and this voltage will need to propagate along the wire to this location, and then you get the data. This data's output signal will go here to the synthesis amplifier to amplify the data to digital 1 and 0. So basically the distance you need to travel is going to increase. The RC delay is going to increase along those wires. So basically row and column is those wires, word line and bit line wires, the interconnect. So the larger capacity means the larger small ti as well. And another way to keep the MI low is to use smarter management policy. So how do you replace the data in this level I? So this is a topic of the computer architecture course. We are not going to discuss in more details. So basically, you want to keep the most frequent used data in this level I. You need to predict what's going to happen in the next. You want the data you want to be stored in this level as much as possible. So for example, you can count the frequency you use the data. So you want to keep the most frequent used data here, or you want to keep the recent data you used here and pick out the older data. So those are the topics for the cache policy in the computer architecture courses. And then you can also keep the big Ti plus 1 low. So you want to basically improve the lower level latency. So here we have one example to show this hierarchical analysis for the latency. This is an old CPU, Intel Pentium 4, and it was fabricated 90nm load. And in this particular case, we only have 2 levels of cache, and the third level is actually the DRAM main memory. But anyway, we call this is level 3. So here the assumption is that you can find all the data in the level 3. All the data can be found in level 3. So that means the miss rate of the level 3 is 0. You can find all the data you need in your program in the main memory in this case. So here the L1 cache, the clock cycle is 4 cycles to access the data from L1, and 18 cycles from L2, and 180 cycles from the main memory in this case, like the level 3. So then we consider, for example, the miss rate for L1 and L2 both are 10%, 0.1. Then what is the perceived access latency for the level 1 and level 2? So here, what is this T1 and T2, big T1, big T2? So how do we approach this kind of question? We have to use that recursive latency equation before, but we have to do it backward from the lower level here and then up. So we can get the T2 first, big T2, because this will be the intrinsic small T2 plus the miss rate of the T2 and then T3. So here this basically means T3 is the same as the small T3. So the T2 here is 18 cycle plus 0.1 miss rate times here, if you want to go to the main memory, you need to spend 180 cycle. So it's 18 plus 18, so it's 36. So that's why we have 36 here. So only after you get the T2, then you can go to the big T1. That is the T1. Oops. Plus M1 T2. So the small T1 here is 4 and then 0.1 times this 36. So if you do that, it's 7.6. So you perceived access time. That means on average, you are going to spend 7.6 cycles to get the data from the level 1 cache, although the intrinsic cycles are only 4, because you many times you often miss the data. So here we can have different scenarios, and then you can redo the calculation. I will skip that. If you reduce the miss rate, then you can improve this. So any questions? All right, next we're going to spend a few words on the DRAM scaling. So the DRAM is a different technology than the logic transistor, and they are actually made by different foundries. So like TSMC is not going to make DRAM for you. DRAM is a special technology. And the DRAM scaling, like the key feature, the dimensions of the DRAM cell also exponentially reduce over the past few decades. And today the DRAM's feature size is about like 12 or 14 nanometer. So it's an exponential decrease. And as a result, the DRAM's cost is lowered. So $1 here, how many bits you can buy? So nowadays, with $1 you can buy like 1 gigabit, for example. So this is also an exponential trend. So if you compare the DRAM and logic transistor we talked about earlier, the dimensions, the key feature size, exponentially decrease over the years. So the scaling works both for the logic transistor and also the DRAM cell. But there is a key difference here. That is, the performance does not scale proportion to that dimension scaling. So here the performance, we care about the DRAM access time or the bandwidth, how many data you can fetch from the DRAM at the same time. That is the bandwidth. Therefore, there is a memory wall problem in today's computer architecture, where the CPU performance outpaces the DRAM's performance. So here this is normalized performance, CPU versus the DRAM. So we see there is a gap, and this gap is enlarging in the past 20 years. So this is the so-called the memory wall problem, and this is also called the von Neumann bottleneck in today's computer architecture. So here the reason is that a CPU nowadays, because of the parallel processing, have multi-cores. So the CPU's capability in terms of the processing throughput is much larger than what you can get from the DRAM through the data bus. Because through the data bus width is limited, and therefore you cannot get the data efficiently. The CPU has to wait for the data to transfer from the DRAM. Therefore, there is a memory wall problem, like there's a wall between the processor and the DRAM. And that is a bottleneck of today's system, especially for the data-intensive workloads. For example, if you are doing the training of the machine learning algorithm, then the data is very data transfer is very intensive. For example, here we have an old system in the 1980s. The clock frequency for the processor is like 10 megahertz at that time, and DRAM memory access latency is 1.2 microseconds. And today, the processor's clock frequency can be up to 3.6 gigahertz for the high-performance server type processor. So here you see that the clock frequency increased by 360 times, but the DRAM access time decreased from 1.2 microseconds to 40 nanoseconds. So this is like 30x. So your processor improved by 360 times, but DRAM only improved by 30 times. Therefore, the processor outpaces the DRAM's performance. And we are seeing this problem right now in today's computer architecture design. So any questions? Okay, so today is an overview of the memory subsystem, and just want to emphasize a few key points. The first one is understand the memory hierarchy, why we need different memory technologies here, why we need so many levels, because we have the trade-off between the capacity and the speed or the access latency. And then understand the memory cell area metric, the F square, and then be aware of those typical numbers for different technologies to store 1 bit information. How many F square you need to spend to store 1 bit. And then here understand the generic organization of the memory chip. So you have the memory cell array, rows and columns, and then we have peripheral circuits. And then this hierarchical latency analysis, and understand this equation, and how to apply that equation to this kind of problem. So I got one question: what happens when the CPU outpaces the memory? So the CPU has to wait for the memory. So you have some idle time for the CPU to wait for the data from the memory. But I have to say, in the past few years, the industry has really made progress in the DRAM interface. So nowadays we have the so-called high bandwidth memory (HBM) interface, which basically provide very large bandwidth. If you look at the GPU system, for example, NVIDIA, like the Titan RTX GPU, it has built-in like a memory and packaged on the same, I would say, the same package. So try to make the two chip, the CPU chip and the memory chip, packaged within the same package. Then make them closer and make the interface wider, so you can access the data more in parallel fashion. Therefore, you can afford this large memory bandwidth requirements. You can satisfy that by some innovations in the interface between the memory and the processor. I think there are some progresses there. So if you look at the GPU system, that is a good example, because the GPU needs a lot of memory, especially when you do this machine learning training kind of workloads. So I think the industries are doing something to make this gap between the memory and CPU closer. And actually, in my research group, what we are doing right now is to make the memory computation and memory together. So we call it in-memory compute. So we don't separate the processor and memory. So what we are trying to do is to do the computation directly on the data. So this is a hot research topic that the academic groups like us are researching. So I think that will be the future of the computer system. All right, so any other questions? If no, then we will stop here. Thank you. Bye-bye.